welcome to Lab 4 Oscillations. We'll take a closer look at spring mass system, oscillation, and derive data from the change in energy and position. To start, we'll review relevant principles and formulas, then we'll use Tracker to analyze the system. Next, we'll use ClosScript and data from Tracker to create a computational model. We'll then compare the predicted and observed motion of the mass and the plot energy changes. We'll close with some quick discussion. The relevant principles and formulas are listed below. So Newton's second law is the classic net force equals mass times acceleration. We could derive the change in momentum is equal to the net force times the change in time with this. Additionally, we have Hooke's law, so the force of the spring is equal to the spring constant times -1 times the stretch. We also have the energy principle, where the change in energy is equal to the sum of the change of all the types of energy within the system. So we'll be looking at kinetic, potential gravitational, and potential spring energy with this example. So we have our tracker video right here. As you can see, our origin is defined up here. We know the length of the wall at this point to help build a frame of reference to calculate where all these positions are. As you can see, there's a position time graph for both the x and y components, and they're compiled in the graph right here. Okay, so on to ClosScript. With this, we know that the mass of the ball is 0.402 kilograms. This was given. From the ClosScript animation and data, we were able to find the initial position. We know the vector for velocity starts at 0 because the initial velocity is 0. I put the initial time to be 0 to make life easy. This is associated with the frames per second. The gravitational constant was given. We found the spring constant through 4 times pi squared times the mass over the period squared. We found the relaxed length of the spring through the magnitude of the length, so 0.7, minus mass times gravitational constant over the spring constant. Next, we have these formulas. So the length is equal to the ball's position minus the spring position. This is just the directional version of this, because we divide by the magnitude. The stretch is equal to the magnitude of L minus the relaxed length of the spring. These are the formulas for energy within the system. So 1/2 mass times velocity squared. We have potential gravitational is equal to mass times gravitational constant times the y position. We have potential spring energy is 1/2 times spring constant times stretch squared. And the energies, again, all the components of the energy added together. So the video ends at 9.5 seconds. That's why I defined t within that boundary between 0 and 9.5. This is self-explanatory. The k initial can be defined as k. Same for all the other types of energy. We have the gravitational force only affecting the y component because it's equal to the negative mass times the gravitational constant. The force of the spring is the negative spring constant times the stretch times the force of the spring's movement. Times the direction of the spring's movement. The net force is the force of gravity plus the force of the spring. This is because these are the only two forces within the system. Again, the system includes the spring, mass, and earth. Right here we have the velocity update formula, so initial velocity plus the change in velocity calculated this way. Position update formula, so initial position plus change in position. We already went over these, and it's just repetition within the code. And I also sped this up to make the animation move a little faster. So here we go. We see the yellow dot's the origin, the blue is the predicted path by the computational model, while the red is the actual observed motion we saw through Tracker earlier. Next, we have the graphs to show this movement. You see a slight variation between these two. This is because we neglected to include some forces in our calculations, like the force of friction, air resistance, thermal energy, and other dissipative forces. To the right, we see the change in energy versus time graph. It's important to note that the change in energy is 0 because the energy is constant within the system. So with this, the energy principle is satisfied because, again, this energy is constant and this holds to be true. No energy was created or destroyed. It was transferred between these values through the oscillations. All right, more discussion because I really like talking. So estimate the oscillation periods of the x and y components. So I estimated these two values, and you see that for the x, this is slightly larger. I believe this period of oscillation is slightly greater because the mass travels a greater distance along the horizontal axis. This may also be a result of error previously discussed. Thank you for your attention and have a great day.